Cool, hello and welcome back to another walkthrough video. Today we're going to be going through the 2024 Edexcel Higher Paper 2. If you've come here just to look at a particular question, there's some timestamps below, so feel free just to go and click on one of those and see where it takes you. But look, if you're here to go through the whole paper, let's dive in and we'll see how we get on. So here we go. So question 1, what do we got here? We have got a right angle triangle. And we're trying to work out the length of CB. Cool, okay, so CB's down here. Nice, it's a right angle triangle. Right angle triangles, either we're looking at Pythag or SOHCAHTOA. This is a case where we're doing Pythag. We got 3 sides. Cool, so into calculator, we're just going to want to put 19 squared minus 10 squared and square root it. Cool, I'm just going to have to power through doing that. 19 squared minus 10 squared. Boom, 3 root 29. Or in other words, we're looking for 16.2. And that's to 3 significant figures, that 0.15 rounding up to 2. Good thing to check with these as well is that you always want your answer to be shorter than the hypotenuse. So notice that 16.2 is less than 19. Cool. All right, off to a good start. 90 is a product of its prime factors. Cool. So with these, what we're going to do is we're going to try and identify all its factors. And we stop on its branches once we reach prime numbers. My favorite method for doing this is always start by dividing by 2. Always keep on iterating, dividing by 2. If you can't divide by 2, divide by 3. Can't divide by 3, divide by 5, so on and so forth. So here, 2 and 45. Does 45 go into 2? No. Does it go into 3? Yes. 3 and 15. Rinse and repeat, right? 3 and 5. Oh, and look at this. We've hit each of our limits on the branches. We can't break these into any smaller numbers. So therefore, 90 as a product of its prime factors is 2 multiplied by 3 squared multiplied by 5. You could put that back into a calculator just to double check if you wanted to. Nice. Next up, the lowest common multiple of A and B. Interesting. These are both pretty nice numbers. So sometimes you might want to fire through that Venn diagram method where common prime factors multiplied together will give you the highest common factor, and then multiplying everything in your Venn diagram would give you that lowest common multiple. But in this case, let's be a little bit clever with what we've got. 2 squared times 3, that's 12. 2 times 3 squared, well, that's going to be 18. And we're looking for the lowest common multiple. That's the first number that goes into the times table of both of these numbers. So actually we can kind of just start walking through the times tables of each. 12, 24, 36, 48, 60, 18. Would you look at that, right? I think this question was laid out to try and get people to actually do it this way. It's a little bit faster, so 36. It would, of course, still work the other way. But sometimes it's about looking at the questions you've got and going, yeah, I reckon there's a faster way. 1 mark giving you a bit of a hint there. Question number 3. The number of hours H that some machines take to make 5,000 bottles is given by the hours is equal to 72 divided by the number of machines. All right, fantastic. So on Monday, we've got 6 machines that make 5,000, and on Tuesday, we've got 9 machines making 5,000 bottles. How much more time did it take on Monday than Tuesday? Cool. So on Monday, we had 72 over 6, which is going to give us 12 hours. And then on Tuesday, same calculation, it's going to be 72 over 9, which is equal to, what's that going to be, 8 hours. Cool. So it took 4 hours longer, right? Difference between 12 and 8. There are only red, blue, and yellow discs in a bag. There are 24 yellow discs in the bag. Okay, so we're learning some facts straight away. Yeah, okay, so we've got discs. We've got the probabilities as well. Okay, I can see where this is going. So we're going to want to make ourselves a bit of a table just to keep a track of what's going on. So let's say we're going to have the probability row defined by P. And let's say the number of them. So I'm going to use a hash symbol. That's quite common in maths that we'd use a hash symbol. And then we're going to have red, we're going to have blue, we're going to have yellow, and then I'm actually going to have a totals column as well, just so we can keep real track of everything that's going on here. Whoops, there we go. So we've got 24 yellow discs, And we know that the probability of yellow is 0.16. We know that the total probability of red, blue, and yellow is going to have to be 1. And we know this ratio of 5 to 4 here. So we can't really do that much, right, without knowing a total amount of discs in the back, right? We can't split the remaining red and blue discs into this 5 to 4 unless we know what the total is. So that's actually our objective, is to find the total number of counters. And actually hidden in the logic of this calculation here, we can find the total, right? If we had the total counters and we multiplied it by this 0.16, we would have gotten 24. Hence, we can rearrange this, right? Total counters is equal to 24 divided by 0.16. Cool. So we can say this is equal to 24 over 0.16. See what that gives us. 24 divided by 0.16, 150. Cool. So in this box, we've now got 150. So the question remains, right? How many counters are there that are going to be red and blue? Well, that's going to be 150 minus 24, which is going to give us 126. And now we're just going to be splitting them into this 5 to 4 ratio. We want to work out the number of red discs, so we can think of it as though, what fraction of this 5 to 4 are red discs? Well, there's 9 parts total, and 5 of those are red, right? So that means we can think of this as 5 out of a total of 9 are red. Cool. So the probability of it being red out of the 126, not out of the 150, out of the 126 is 5 over 9. So let's power that into our calculator. 5 over 9 times by 126. Boom, 70. Bosh. Okay. Notice we're not filling out everything in the table here. It's a little bit overkill, and maybe actually this question would be a little bit easier without a table. Maybe if you've done it a different way, let me know. But yeah, for 4 marks, nicely worked out. It's not the most straightforward question. Excellent. On to question 5 now. Complete the table of values for y equals x squared minus x. Awesome. So here we're just going to be plugging in our values, substituting in the x values, right, into x squared minus x, and seeing what y coordinate we get out. Remember, all equations, they're all just machines. You're passing in x values and getting out y values. So here, 1 squared minus 1. Oh, well, that's going to give us 0. Nice. 3 squared minus 3. 3 squared is 9. Minus 3 is going to be 6. And careful with this minus 1. I can see that this is going to catch a lot of people out here. So minus 1 squared is going to give positive 1. And then minus 1, right? In this x over here is also going to be positive 1. Those negatives becoming a positive. And hence we're going to get 2. Sweet. And you'll actually start to notice there's a little bit of symmetry between our y values. Not always true, bear in mind, but quite common. Nice. And then from here, we're just going to plot all of these onto our graph. So this is just an exercise of plotting coordinates. Minus 1, 2, there it is. 0, 0, cool. 0, 1, nice. 2, 2, there it is. And 3 across 6 up. Look at that. Nice quadratic. And we ought to really just give this a bit of a sketch. Oh, I've gone missed that one, but hey ho. And back out the other side. Oh, there we go. Cool. Hopefully you can do that a little bit better on paper. It's a little bit hard for me to do it. Sweet. And then part C says, use your graph to find estimates for the solutions of the equation x squared minus x equals 4. Okay, a little bit of background understanding. What is this asking? Well, previously our equation was saying we had y equals x squared minus x, right? And that's what we've plotted up here. But let's say we also theoretically had the equation y equals 4. Well, what do you notice? Well, because both of these are equal to y, they can be equal to each other. So this question here can actually be decomposed into 2 equations themselves. Y equals x squared minus x and y equals 4. Now we've already plotted this x squared minus x. That's the graph that we see here. And all we need to actually do in this remainder of this question is plot our y equals 4 line. That's just going to go across like this. Now, we're not quite there. We haven't quite got our answers. Use a graph to find estimates to the solutions. Solutions in this case means what are the x values that work for both of these equations where they're equal? And that, of course, is going to be where they cross. What are these x values? There we go. And we've got another one over here. So as a rough estimate, I'd say that we're looking at a negative x value of about minus 1.6 and a positive x value of about 2.6. They're approximations. Maybe when you draw it, you might get, I don't know, 0.1, maybe 0.2 out of what I got there. But yeah, good approximations. Sweet. So Andy, Luke, and Tina share some sweets in the ratio 1 to 6 to 14. Okay, that seems useful. Let's start writing that out. So 14, Andy, Luke, Tina. Nice. Tina gives 3/7 of her sweets to Andy. Okay, I can see this. So we're going to go through stages. So if Tina's giving 3/7 of her sweets to Andy, well, we've got 3/7 of 14. You might need a calculator to figure this one out, but you can also think about scaling up this fraction. Multiplying top and bottom by 2 would give 6 out of 14. So in other words, she's giving 6 to Andy. So that means that Tina's going to lose 6. Let's just put this as a placeholder, and Andy's going to gain 6. So this is going to become 7 to 6. This one's not changed, has it? And then we're reducing 6 off Tina, so she's got 8. Okay, done. We've ticked off that step 1. Tina then gives 12.5% of the rest of her sweets to Luke. Okay, 12.5%. Oh, that's not very nice. If you were to plug this into your calculator as 12.5 over 100, it would actually automatically tell you that this is the same as an eighth. And I think that's probably the nicest way to go about this. So in words, Tina's giving 1 out of her 8 counters or sweets to Luke, right? So she's once again losing 1 here, not 6. That was last time. Losing 1, and Luke is gaining 1 this time. Cool. So now we have 7, 7, 7. Tina says that now all 3 of us have the same number of sweets. Absolutely, she's correct. We know that they've all got some multiple of 7. They don't necessarily have 7, but they've got some multiple of 7. Cool. Okay. On to question 7. ABCD is a quadrilateral, 4-sided shape. All angles are measured in degrees. Show that ABCD is a trapezium. Cool. So, how are we going to go about doing this? Well, the trick for noticing if something is a trapezium is the angles on one side must always add to 180. And this is going to be true of this side as well. So we're going to want to show that. But currently everything's all algebraic and a bit confusing. So let's see if we can actually figure out how big these angles are. Now we're dealing with a quadrilateral, and that means that it's going to add up to 360 degrees. In other words, all 4-sided shapes have 360 degrees inside of them in their interior angles. You might know this as a fact. There is also that formula, the n minus 2 times by 180, which can give you this. So we know that 360 degrees is going to be equal to the sum of all of these angles that are visible to us. 2x plus 15 plus 4x plus 15 plus 4x plus 8 plus 3x minus 3. Cool. Let's combine our x's. There's going to be 8x there plus the 2. That's going to be 10 plus 3. That's going to be 13x. 15 plus 15. Here we go. 8 minus 3 is going to be 5. 15 plus 15 is going to be 30. So plus the 5 is going to be plus 35. 360 equals 13x plus 35. Cool, a little bit closer now. 325 is going to be equal to, that's taking the 35, is going to be equal to 13x. And therefore, or you might be able to spot this, you might not, but 25 is equal to x. You've got a calculator, so 325 over 13. Cool. So just going back into our quadrilateral, just to show that it's a trapezium, we need to make sure that angle A plus angle B is equal to 180. You could also show that angle C plus angle D is equal to 180. But let's show out just A and B. So angle A is going to be equal to 50 plus 15, which is going to be 65. And then angle B is going to be equal to 4 times x, so 100 plus 15. So 115, and look at this. Summing these together does indeed give us our 180. Cool. So therefore we've shown it's a trapezium. And maybe a little bit more context as to why that is. Your parallel line rules tell you that this is parallel to this. That's what defines a trapezium. The line A to B and the line D to C are not necessarily parallel, but B to C is parallel to A to D, which means that you actually have a co-interior angle on both sides, right? And if you remember your co-interior angles, they must add to 180. Question 8. We have a playground that's in the shape of a right angled triangle. How wonderfully fitting. And Dan makes a scale drawing of the playground. He says that 1 centimeter represents 5 meters. The area of the playground is 28 centimeters squared, and the real length of QR is 40 meters. Okay, let's label stuff on. So this is 40 meters, and 1 centimeter represents 5 meters. Cool. And we know that the area is 28 centimeters squared. So that means that sum half times by the base times by the height is equal to 28. Now, if 1 centimeter represents 5 meters, we can say that this is the same as 8 centimeters, right? 8 times 5 meters would give you 40, yes? So we can say that a half times by our base times by our 8 is equal to 28. Let's tidy this up and solve for b. b times by a half of 8, 4 is equal to 28. So b is equal to 28 divided by 4. Let's just smash that into the calculator. 7. Nice. So there it is. Our base is equal to 7 centimeters. And now all we need to do is work out the real length of PQ. And remember, we've got this ratio. 1 centimeter equals 5 meters. We have 7 centimeters, and therefore we have 35 meters. Nice. Now on to question 9. A number n is rounded to 2 significant figures. The result is 7.3. Write down the least possible value of n. All right, this is 7.25. Right, anything less than this would round to 2 rather than up to 3. Leela says the value of n cannot be greater than 7.349 because 7.350 would round to 7.4. Interesting. Is she correct? There are numbers greater than 3.49, right? Sorry, 7.349. So no, I'd say she's incorrect. You could have 7.3495, for example, which is greater than 7.349, but this still rounds to 7.3. So is she correct? I don't think so. There are bigger numbers than 7.349 that still round to 7.3. On to question 10. 2 right-angled triangles, both of which look quite algebraic. All lengths are measured in centimeters. Okay, fine. Given that sine of A is equal to tan of B. Oh, fantastic. Okay, so we're going to be equating sides in some sort of algebraic equation here. Now, from your SOHCAHTOA, you might remember that sine of A is equal to SOH, opposite, over your hypotenuse. And tan, well, that's TOA, isn't it? So tan of B is going to be equal to your opposite over your adjacent. So actually, we can say that sine A equals tan B is exactly the same as saying, well, the left triangles, opposite and hypotenuse, is equal to the right triangles, opposite and adjacent. In other words, 7 minus 2x over 8 is equal to, opposite, 1 plus x over 4. Excellent. Now from here, all we need to do is solve the algebraic fractions. First step is going to be to cross multiply. In other words, multiplying top and bottom multiplying the top of this equation by 4 and multiplying the top of this equation by 4 would give us 4, 7 minus 2x. And moving the 8 across the other side, we'll do this at the same time, is going to give us 8, 1 plus x. Cool. Now we've gotten rid of those fractions. Life's going to be a little bit easier for us. 4 times 7 is going to give us 28 minus 8x equals 8 plus 8x. And then let's get all the numbers to the left-hand side. So 20 is going to be equal to 16x. There you go, your answer, 20 over 16 is equal to x. They might want this simplified. You can simplify it down to 5 over 4. Nice, tough for 3 marks. So yeah, there you go. The frequency table gives information about the weights of 60 parcels. For part A, we want to complete the cumulative frequency. So cumulative frequency is just where we add all of the existing frequencies up to and including that point. So all of the frequencies between 0 and 2, well, that's just 7. But all of the parcels between 0 and 4, well, that's going to be 7 and the 21s. So 28, so on and so forth. So we're just going to power through these. 43, and then would have 54, and then 60. Nice. And then for part B, on the grid opposite, draw the cumulative frequency graph. Okay, cool. So the way to do this is we look at our cumulative frequency, and we know that by the time we hit 2 kilograms, right, there must be 7. By the time we hit 4, there must be 28. By the time we hit 6, there must be 43. We don't know exactly where they are, though, right? So we've got to be a little bit selective with how we do this. We can't be putting these crosses right in the middle, or else we would be cutting off some of the values that we might have wanted, which is not how we want to go about this. Here we go, just plonk them all on, 54 and 60. And it's actually really important for me to note that sometimes they might give you different gaps between your weights. Here they've been pretty nice. Each is a 2 kilogram increment, but I've seen papers where they might do like throw in a 4 kilogram increment without people realizing. Cool. And then from here, all we need to do is just basically play dot to dot. All right, we're just going to connect all of these together. And very important that each of these just goes between both the dots. Cool. There we go. Nice. So part C here. Use your graph to find an estimate for the interquartile range. Well, the interquartile range is just looking at the middle 50% of weights. And to do that, we need to identify what the 25% like smallest parcel would have been and the 75% biggest parcel. Now to figure that out, we've got to work out, well, what number would have been the 25% biggest or smallest parcel out of the 60 parcels we had? And that would be 60 divided by 4, so 15. So the 15th parcel would have been the like 25%, and the other side of that would have been the 45th% parcel. So we can use this as a way to figure out what those weights would have been. Now, of course, these are slightly missing our exact points. So this is a wonderful way of estimating what we would expect to see for our interquartile range. Let's say that this one here is looking like, let's say 2.6. And then this one over here is looking like 6.6. So there you go. We see a bit of a gap of about 4 kilos. And then part D, use your graph to find an estimate for the number of those parcels with a weight greater than 7.4 kg. Amazing. So to do this, we're actually just going to look at our graph and go, oh, okay, let's do it backwards. 7.4 kg, that's going to be right here. We're just going to work our way up to the line, there it is. And if we go all the way across, that gets us to about here. It's about 51. So use a graph to find the estimate for the number of those pulses with a weight strictly greater than 7.4. So we're going to say that there's 8. Where the 51st is exactly 7.4 kilos. So there's about 8 bigger. Nice. On to question 12. F is inversely proportional to D squared. F equals 3.5 when D is 8. Cool. So to do this, we want to put together our equation. You might have seen these done with this sort of proportionality fish symbol. So F is proportional to 1 over D squared, which means that F is equal to K over D squared. And now it's our objective to identify what K is, right? And we can do this by plugging in the values that we have. 3.5 is equal to some value K, some constant, over D squared, 64. Multiplying up by the 64 times by 3.5, we get K is equal to 224. So there's our equation. Find an equation of F in terms of D. F is equal to 224 over D squared. Part B, find the positive value of D when F is equal to 10. Okay, cool. So to do this, we're going to have to just quickly rearrange. So if we started with F is equal to 224 over D squared, well, we can multiply by the D squared and get F D squared is equal to 224, and then divide by the F. D squared is equal to 224 over F. And then lastly, to get D by itself, well, I'm going to have to take the square root of this thing, 224 over F. And importantly, this square root, it could be positive or negative. Remember, squaring negative numbers yields a positive answer, D squared, right? But in the question, it says, I only want the positive value. So we're just going to take the positive value of this thing. So typing into your calculator, 224 over 10. Oh yeah, make sure you've got that within a square root. And there it is. I got 4.73. Okay. Next up. Question 13. On the grid, shade the region R that satisfies all of the following inequalities. Oh, okay. So let's just work through these one at a time. X is less than or equal to 2. Okay, that's going to be, find X. X is 2, there it is. And we want all of the values of X that are going to be less than that. So let's draw our vertical line. Try and do this as well as possible. And we want everything that is going to be smaller, that way. I'll draw some arrows on there to make sure we remember. All right, that's that one done. Y is greater than or equal to 3. Cool. So where's that going to be? That's going to be down here to -3. Cool. And I want everything going up this way. Nice. So we're already finding a region down here that we don't want, but we do want everything over here. Okay, excellent. Next one. Okay, now we're getting into our straight lines. Y is less than 2x plus 1. So let's start by just plotting 2x plus 1. And we know that's going to go through a y-intercept of 1. And for every step it goes to the right, it's going up 2. That's our gradient. So here we go. We can just plot on some points here, figure out where it's going. Cool. That's enough. I don't need to go any further than this. I could, but these ones are what we need because they're currently within the region that we're looking for. Now, instinct tells us that we're probably going to be wanting down, right? We're building a triangle in the middle. But if you were ever a bit confused by this and didn't know what was going on, well, you want your y coordinate to be less than the x coordinate, given this equation, right? So you can always check by plugging a value in. Why not? I'll do one quickly. So say we picked this coordinate up here and I wanted to know if it actually worked. Well, this coordinate is -1, 3. And that's like saying, well, is 3, your y coordinate, less than or equal to 2 times -1 plus 1? And this is false, right? It's true or false. And if it's false, well, then that's not the region I want. So there's always ways to check these values. It's good to know how to do them. So yes, we want this way from this line. And then last but not least, this one. And I feel like this is the one that would probably catch people out. Currently, it's not in a very nice form, but we can rearrange it. So 2y is less than or equal to 6 minus 3x. Okay, negative gradient in this case. And actually, let's just say that this is 2y less than or equal to minus 3x plus 6. Therefore, we've got it in that y equals mxc plus c form. And if we do y is less than or equal to minus 3 over 2x plus 3. There we go. So negative gradient, but it's going through positive 3. So there it is. It's going through positive 3. And what's this saying? Well, it says it's going down, but for every step I take to the right, I'm going down 1.5. Or in other words, for every 2 steps I take to the right, I'm going down 3. So let's do that. Every 2 steps I take to the right, I go down 3. Every 2 steps I take to the right, I go down 3. And that there is actually going to be enough for us to plot on our graph there. Now, once again, we want to make sure that our y value is less than the line, which indicates that we want all of these y values down here. And this has got a little bit untidy, but our region that we're left with is this one in here. Cool. Nice. Okay, on to question 14. The graph shows the velocity of a car in meters per second, t seconds after it starts to slow down. Okay, so we're starting at a high velocity and it's slowing down to no velocity, it's braking. Calculate an estimate for the acceleration of the car when t is equal to 5. You must show all your workings. Okay, so in an exam, what you'd be doing is you'd be going, cool, to find the acceleration, I need to know what the gradient is. How steep is my curve at t equals 5, right here. So you grab your ruler and you'd roughly estimate what it is. I'm going to try and sketch it on, something like this. And your objective is usually to try and find some coordinates that this line goes through. There's one about there that I think is nice. That's going to be about 310. And let's see if we can find another that it's quite nicely going through. Maybe just maybe we can get away with this one over here, which is going to be about 7 across and 2 up. Cool. So it's always an estimate, you know, it doesn't matter too much. But you must get your gradient correct. And to do your gradient, you want to do change in y over your change in your x coordinates. Now, I always like to consider how far I'm moving always to the right in my x coordinates. Getting this sort of consistently is a nice way of doing it. So I'm always moving some positive direction in the x value, right? It's going positively in time. Right, if you're a bit happy with sciences, it's kind of nicer to think that you're moving positively in time. So this is going 4 to the right, or 4 as a change in x, and our change in y is a decrease in 8. So if we were to just plot these in, change in y, that's decreasing by 8, and our change in x is positive 4, well, we get minus 2, which means that our acceleration is minus 2 meters per second squared. Cool. Work out an estimate for the distance the car travels in the first 6 seconds after it starts to slow down. Use 3 strips of equal width. Okay, for 3 marks, this is all right. We're just going to be finding the areas of 3 trapeziums. I'll use a blue in this question to make it a little bit clearer. So here's going to be our first trapezium, our second one here, and, oh, sorry, that should be a little bit further down over here. And then our last one is going to be all the way over here. Cool. So we're just going to work out these trapeziums. And if you remember the formula for trapezium, it is a plus b over 2 times by the height. Now we're looking at our trapeziums sort of rotated. This way is going to be our height typically. So it's always going to be 2. And then our a plus b, well, that's going to be the 2 parallel sides. So we're just going to be adding 25 to this value here. Looks like 16. And then we're going to repeat that for each of these. This one here looking a bit like 9. And then lastly over here, we've got 4. So I'll do this in blues. I'll just write down everything that's going on. So our first trapezium, number 1, is going to be 25 plus 16 over 2 times by 2. Oh, look at that. They're going to cancel, aren't they? That's wonderful. And then We can rinse and repeat this. The second one is going to be, what's that going to be? 9 plus 16 over 2 times by 2. And then the third one, 1, 2, 3. Oh, it's quite a lots of drawings going on this question. And the last one's going to be this 9 plus 4 over 2 times by 2. Cool. So if we were to work through this really nicely, we'd actually end up with, what's that going to be? 41 over 2 multiplied by 2. So they're going to cancel. So we're just left with 41 for this one. The same kind of thing is going to happen here. This is going to be 25. And lastly, exactly the same thing again. This is going to be 9. Then we can just smash all of those together. Why not use a calculator? Save yourself a moment. And these all sum to 75 meters. Cool. All right then. Next up, given that a is a prime number, rationalize the denominator of 1 over root a plus 1. Okay, fantastic. So this is a rationalizing the denominator question. And we've got a slightly more complex denominator. It isn't just the square root. So we're going to have to flip the symbol there to a negative when we multiply it. So the trick is that we're going to take our original surd like this, and we're going to multiply it by root a minus 1 over root a minus 1. And notice that regardless of the value of a, this fraction is going to be 1. So we're technically not changing the original fraction, right? Multiplying anything with 1 keeps it the same. On the numerator, we're just going to end up with root a minus 1, but on the denominator, we're going to end up with root a plus 1 multiplied by root a minus 1. I'm just doing it off to one side here so we can run through the maths. So root a times a is going to give us a. Root a times minus 1 is going to give us minus root a. 1 times root a gives us positive root a. And 1 times minus 1 gives us minus 1. Notice these two bits in the middle are going to cancel, and we're just left with a minus 1. Boom. There it is. Can we simplify that at all? No, not really. I wouldn't dwell on that. There you go. For 2 marks, you'd leave it there. Okay, next up, question 16. We have got a quadratic inequality. Quite early to be seeing one of these. But fundamentally, what it's saying is you've got 2 equations. Y is equal to this quadratic, and you've also got y is equal to 0, right? Roughly speaking, you've got a graph. There's going to be some quadratic. Let's not even dwell on what it looks like at the moment. We can come back to it. And it's going, well, there's your quadratic, and here's your y equals 0. Can you tell me the values of x for when your quadratic is less than 0, i.e. this bit under the curve? So you just want to find the points where it crosses the x-axis, and then we want the region in between. Okay, so let's come back to this idea in a moment. Let's run through the maths. So to find our roots of this quadratic, let's not dwell too much about anything else at the moment. We've got 4x minus 3 and x plus 5. And to find our roots, well, we can set this equal to 0. And we need to consider when each of these parts is equal to 0 as well. Think of this like a multiplied by b, where a is this value and b is this value, is equal to 0. The only way that 2 numbers or 2 values multiplied by each other could equal 0 is if one of them themselves is 0. Hence, we can break this into 2 equations. 4x minus 3 equals 0. And x plus 5 equals 0. As such, 4x equals 3 and x is equal to 3 over 4. Excellent. There's one of our roots. And the other one, this one's a little bit easier, x equals minus 5. All right, cool. So there we go. We have our roots. We've got one a little bit further over here and then one a bit closer to our x-axis. So this is going to be our 3 over 4. And this over here is going to be minus 5. Excellent. And then to get our inequality, well, like we said earlier, we just want to find the region in between these 2 values. Yeah, because it's less than y equals 0. That's essentially our x-axis. So our solution is I want x that is less than 3 over 4, and I want x's that are greater than minus 5. Quite tricky for 2 marks. On to question 17. L, M, and P are three similar solid shapes made from the same material. L has a mass of 64 grams and M has a mass of 125 grams. M has a total surface area of 144 and P has a total surface area of 16. Cool. So let's try and compare these values and see what we can do. So L to M have masses of 64 grams to 125 grams. Now, masses are a metric of the internal area of these shapes in a similar way to volume, right? So you can think of this as a volume-like scale factor. So to be able to get the linear scale factor from this volume scale factor, right? Look at this, right? We want to find the heights of each. That's a linear scale factor. We want to take the cube roots of these. So we need to think about what the cube root of 64 is and the cube root of 125. I'm just going to write this to the side, cube root. And doing the cube root of 64, well, that's going to give you 4. And the cube root of 125 gives 5. Awesome. Now working through in a similar way for M and P, we now have surface area or an area scale factor of 144 to 16. And to get from an area scale factor to a linear scale factor, we take the square root. Okay, leaving us with 12 to 4. Now then, to get back to our value that is going to be our shared ratio between these three values, we need to consider how we can put these into one thing. 12 and 5, they're shared by M, but we need to find a value that is actually a little bit easier for us to get to. That looks like it's going to be 60. We're going to have L to this side, P on this side. We've multiplied 12 by 5, so P is going to get multiplied by 12, giving us 20. And 4 on this side is going to get multiplied by 12. 5 has been multiplied by 12, so 4 by 12 gives 48. Can this be simplified? Yes, it definitely can. All of these values can be divided by 2, so we get 24 to 30 to 10. Oh, look at that, they can all be divided by 2 again, giving us 12 to 15 to 5. Cool. Question 18. There are only 4 red counters, 3 yellow counters, and 1 green counter in a bag. Tony takes a random 3 counters from the bag. Work out the probability that there are now more yellow counters than red counters in the bag. Oh, that's a tough one, right? Because you need to think about, is it best to do it through a tree diagram? There's a lot going on at play here, right? We're taking 3 counters and there's 3 options, right? It's going to get pretty complicated that way. So maybe we can be a little bit smarter about what happens. Now, the objective for us is to think about, well, what possible ways are there that we could end up with more yellows than there are reds? And, well, objectively, right? That means that the red counters at the end must be less than or equal to 2. That's our objective, assuming that there's still 3 yellow counters. So let's think about how that could happen if we only took out 3 counters. Well, it's clear that at least 2 of them must be red, right? Because we need to get from 4 to 2. But if that third counter was a yellow one, then we'd have 2 red and 2 yellow. But that isn't strictly like less red than there are yellow, or more yellow than there are red, right? That's a strict, right? It's not, they can't be equal either. So it must always be a green one that we're taking, or we're taking 3 red counters. So this question's actually been a bit more problem-solving logically with what's going on. than using any diagrams. But let's walk through it. So if I took out, let's say 3 red counters, let's just say out red, 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 I would end up with 1 red, 3 yellow, 1 green, right? And that definitely is less red than yellows. Okay, the next one is going to be, let's say red, red, then green, right? What would happen this time? Well, we've got 2 reds, 3 yellows, and we've just lost the green. But that's okay, because reds are still less than yellows. And then we also need to consider the order that we take this out. Red, green, red, and green, red, red. Remember, order matters. And we'd get the same 2R, 3 yellow, 2R, 3 yellow. And that's it. There is no other way that you could take out 3 counters and cause there to be less reds than there are yellows. So now what we need to do is just think about the probabilities of each of these things happening. Cool. So in total, we have 4 plus 3 plus 1, 8. Okay. So what's the probability of the first counter being taken out being red? Well, it's going to be 4 out of 8. It's going to be the probability of the second one being red. Well, we've reduced the number of red counters by 1. We've taken it out, but we've also reduced the total. 3 over 7. And then the same logic applies for the last one. 2 over 8. We can then run through this idea again. 4 over 8 times by 3 over 7. But now we're thinking about a green counter being the one that we take out last. And there's only one green counter. I realise I put an 8 over here. That shouldn't have been an 8. That should have been a 6. And that's the green counter over here is going to be 1 over 6 as well, right? We've taken out 2 counters previously. And this logic continues once again. 4 over 8 multiplied by 1 over 7 this time over the remaining red counters, 3 over 6. And last but not least, the 1 out of 8 for the green originally multiplied by the red counter, 4 out of 7 times by 3 out of 6. Amazing. And now, to get our answers, we're just going to multiply each of these together. Notice all of the denominators are going to be 8 times 7 times by 6. Maybe it's better just to power through doing each of these in your calculator, and we'll see what we get. So we've got 4 over 8 over 3 over 7 times by 2 over 6, and that gives us a 14th. Next up, we've got 4 over 8 times by 3 over 7 times by 1 over 6, giving us 1/28. Next up, 4 over 8 times by 1 over 7 times by 3 over 6, 1 over 28 again. And last but not least, well, this is actually just going to yield the same value once again. We've just changed the order of the 1, 4, 3 in the numerator. So actually you'd get exactly the same value. This here is the same as 2 over 28. So we've got 2 28ths plus 3 28ths down here, giving us a final value of 5 28ths. Whew, that's tough. That was a very interesting and unique question. But well done. Okay. Here's a question. The diagram shows the quadrilateral OACB. M is the midpoint of OA and N is the point such on BC such that BN to NC is 4 to 5. Okay, that means that the distance from B to N is 4/9 of the total distance, and the distance from N to C is going to be 5/9. O to A has a vector of A, O to B has a vector of B, and A to C has a vector of some multiple of B. Right? Let's just write these on as placeholders. It's got B, and then all the way up this way, we've got, just do it like this, little arrow off to the side saying A. So we want to start by expressing M to N in terms of K, A, and B. Okay. So we have 2 different ways of doing this. Either we can go from M to N, down the bottom, around the bottom, and back up this way, or we can go around the top and back to N that way. Now, given I've drawn on this way, I'm going to do it that way. That's going to be our route to get to N. Now, let's really clearly break down how we're going to do this. We're going to start by writing everything in terms of points. So m to n is the same as going from m to o to your origin, plus the distance from your origin to, sorry, that would be over to b, over this way. All right, that's taking us from O to B. And then lastly, from B to N. It's taking us back up here. Now, M to O, we have some information about. We know that M is the midpoint. So we can work that one out all right. We also know O to B straight away. But B to N, we actually don't have very much information about. We're going to have to think about how to do this and how we can approach it. And we know that it's 4/9 of the total distance from B to C. So we can say that we're going to go from M to O plus O to B, and Bn, well, that's just 4/9 of the distance from B to C. Cool. And now we need to ask ourselves, well, how would we get from B to C? We're defining a new vector now. Well, we can go all the way the other way around. We've got to go all the way this way. So B to C is the same as going from B to O plus O to A plus A to C. I like writing out all of the points first and just being very clear with where I'm going, because then you can turn point-to-point notation with vectors in one clean swap. So look at this, right? If we go back up and look at what we've got, well, B to O, that's going to be minus B. We're going in the opposite direction. O to A, well, that's just a 1A. And then A to C is just plus a KB. Nice. So B to C is equal to A plus K minus 1 B. Cool. Now we know what BC is, and we can substitute this into this value over here. So M to O is going to be minus a half A. Right, we're moving backwards in this direction. We know it's a midpoint. Plus O to B is B. And then plus 4/9 of exactly what we found over here. A plus K minus 1 B. Now we've just got to answer this in its simplest form. It's all in vectors. So this is now just an algebra job. So we've got minus a half A plus B plus some 4/9 A plus 4/9 K minus 1 B. How could we simplify this? I'm looking at those A's. Let's see what we can do there. No point worrying about fractions. It's a calculator paper, so let's just plug that in. So we get minus 1 over 18A. And then the B's, yeah, why not? Let's just write this out again. So we've got plus B here. And we're going to get plus 4 over 9 KB. We get minus 4/9 B here. So just expanding everything out. And our final line of workings, we've got minus an 18th A. Then we're going to get plus 5 over 9B plus 4 over 9 KB. Nice. I think that would be in its simplest form. Some might argue that you'd want to refactorize this, have a value of a 9th on the outside or something, but I think that's fine. Part B here then goes, is MN parallel to OB? And the answer to that is no. MN, what we just found, is not parallel to OB. And the reason for that is, well, OB goes in the direction B. Okay, think of B as maybe moving exactly in your X direction. Maybe if it was a column vector, you could think of it as 1, 0. But our movement from M to N, right, also slightly moves in the A direction, right? It's got some movement in the B direction, don't get me wrong, but it also moves in the A direction. And because it does that, it can't possibly be parallel to OB, which only moves in the B direction, right? It's kind of like, think about it on your two-dimensional plane or on your graph. If something's moving only to the right or to the left, and you've got another vector that's moving very slightly up or very slightly down, it can't possibly be going parallel. I think this would be a good enough explanation. So MN moves in the A direction. OB doesn't. Cool. On to question 20. The curve C has equation y equals 2x squared minus 12x plus 7. Find the coordinates of the turning points on C. Turning points, that's going to be completing the square. All right, let's see what we can do with this thing. So, my strategy for doing these is you want to factorize right at the start. You want to factorize a value, so you're looking at a normal completing the square. So I'm going to take a factor of 2 out. We're going to be left with x squared minus 6x and plus 7 over 2. And this is a personal preference. I'd like to just take a 2 out of everything. Just factorizing that 2. And now we can do it with this thing really nicely. So let's just pay attention to what's going on inside these brackets. Remember that we drop the x down. We halve this value, giving us minus 3. We square it. And then we take away the square of this value. So minus 9. And then this value here is just going to drop down, plus 7 over 2. Cool. Now, we're not even thinking about the things on the outside. We're just going to put them there. Big old square brackets. We're not even thinking about it. They're just there. Cool. Let's tidy this up a little bit. So focusing on the inside, x minus 3 squared. Let's do that on our calculator. Minus 9 plus 7 over 2 gives us minus 11 over 2. Cool. Big old square brackets, 2. And now we're just going to reintroduce this 2. We're expanding the brackets. We're going to end up with 2 multiplied by this thing. 2 multiplied by this thing, which is clearly just minus 11. And there you go. That's going to be our completed the square form. And as you'll remember, you flip this one to get your x coordinate. And this value right here is just your y coordinate. By flip, I mean change the sign. So maybe I was a little bit unclear there. That would be a sign change. So our turning point is 3 minus 11. Nice. There is an alternate method where you don't factor the 2 out of the thing at the end, but it's a personal preference. I prefer to, and then reintroduce it entirely in one go. Okay, on to question 21. We have some graph g of x drawn on our diagram here, and we want to draw the diagram of y equals g to the minus x plus 2. Okay, so let's try and identify what these two things do. A plus 2 is going to take every single x coordinate and make our y coordinate 2 bigger. Right? Every time you pass in a value into your equation, it's adding 2 to get your y coordinate. All this is going to do is think of it like your plus c in a linear equation or a quadratic. This moves up. Nice. Then flipping the x to a negative, that's a little bit more complex. Conceptually, think about it like you've got your roots for your quadratic, and you're flipping those roots. You're flipping what your x values are. Now think about it with a quadratic. If you knew what your roots were, maybe you had some quadratic where your roots were 2 and 4, right? If you flip those roots, you'd end up with minus 2 and minus 4, right? Think about that sort of flip. It's actually moving, it's reflecting in the y-axis. And that's exactly what's going to happen here. So we've got a reflection in the y-axis, and we've got it moving up by 2. So let's start by reflecting it in the y-axis. This point over here is now going to end up going right the way over here. Let me do it in red so it's super clear. And this point over here is now over here. We can do the same with our turning point. That's going to be down here. So that's our first movement. That's our reflection. And we're going to have to move all of these up too. So that one's moved up 2. That one's moved up 2. This one is moved up 2. And we've got our final curve happening here. And if we're being really clear, we'd say this is y of g minus x plus 2. Nice. Question 22, and I believe the last one on the paper, is this. We've got 2 tangents. All coming from one point and meeting the circle at 2 points A and B. It is our objective to prove that AP is equal to BP. The length of those two lines, regardless of where P is the same. Now, the way that we're going to do this is by finding a congruent triangle. So, and if they're congruent triangles, it means that the lengths and the angles must be the same all the way around them, right? So let's see what we can do. So we know that from this circle, from O to A and O to B, this length is the length of the radius. Let's call it R. Interesting. And we can split this quadrilateral OAPB into two triangles. There we go. So these two triangles, OAP and POB, share a length. O to A is equal to O to B, since they are radii. Okay, fantastic. A second fact that we know is that the radius from the origin of a circle, or the center of a circle, meets a tangent at a right angle. And this is going to be true for both of our triangles. So 2, OAP and OBP are right angle. And you could explain this by saying it's the radius meeting a tangent, Cool. So there you go. They're now sharing a right angle. Cool. It looks like we're moving towards our RHS angle, or RHS proof of a congruency. There are a few others. Remember, there's angle, side, side angle, and side will all work as well. But we're looking at the RHS, which means that we need to show a right angle. We want to show the hypotenuse is shared, and we want to show that one of the sides is squared. This is our S, this is our R, and last but not least, we need to look at the hypotenuse of both the triangles and see what happens there. And lo and behold, the hypotenuse for both triangles, the longest side, is going to be this OP. And OP is shared. OP shared. So it is the same for both triangles. And that is enough to show that it is congruent. Amazing. RHS, therefore OBP is congruent to OAP. And what does this mean? Well, it just means that all angles plus sides are the same for both triangles. Triangles, which therefore means that AP is equal to BP, since that these are the two lengths that are shared between the two triangles that we haven't actually considered yet. Not the radii, not the hypotenuse, it's the other one. Amazing. And that's it. Cool. I hope that was useful and insightful. If you've got any comments about the way I solved questions or any different ways that you've done it, feel free to comment it below. But otherwise, I'll see you in the next one. Bye now.